can divide those values of stresses, those limits, by a factor of safety and get access to a valuable quantity that we call it a local stress. So and a local stress is a material property. So if we do have a local stress for the material that has been used in the prismatic bar and bolt, we can actually design them. We can find the most optimal cross-section. We can find the lightest cross-section, the least amount of cross-section that can be used for such a metal. So we were in the process of solving this problem. So this is a simple frame system. It's composed of two members. And the problem is asking to design these two highlighted bars, highlighted components. One of them is AB, the other one is bolt at point C. So this was our solution strategy. We first looked at the system, and our conclusion was this is statically determinate, so we can, without knowing the cross sections, we can actually solve for the forces. And we did that. And we find the normal force or the axial force in the member AB. AB is a two-force member, so it can be considered as a prismatic bar. So we actually first calculate the force in that member. Then we use the local stress of 6.20. What was the local stress? The local stress of 20 psi that was given. And based on that, we found a minimum value for the area. So the answer to the first problem, determine the required cross-sectional area of member AB, is this. The area of member AB should be actually at least equal to 0.3125 inch squared. Alright, so and for answering the next question, we need to calculate the shear force that is passing through the pin, because we would like to design this pin. How can we calculate the shear force that is passing through the pin? We need two pieces of information. Number one, we need to know whether that pin is under double shear or single shear. In this case, it is under double shear. Number two, we need to know how much force is applied to that pin. In order to determine how much force is applied to that pin, we need to calculate the horizontal and vertical components of the force that is applied to that pin. So Cx and Cy. We have already calculated Cx and Cy by writing the equilibrium of forces along the x and y axis. So can you guys tell me what is the next step? What should I do next in order to design the pin? Yes? The total force that is applied to C, exactly. In other words, these are components of I can calculate the resultant of these two forces. So actually the force that is actually passing through pin C is going to be the resultant of these two forces, a vector like this, that I can call it actually capital C, not Cx and Cy. So Cx and Cy are actually components of the vector C, or the components of the vector C. So we can actually calculate them. So I'm gonna actually say that C is gonna be equal. Let's focus on this free body diagram. I'm gonna say that C is gonna be the resultant of two vectors of Cx and Cy. So its magnitude is gonna be Cx squared plus Cy squared, and it's going to be square root of 1.25 dips that we calculated plus 5 squared, that again we calculated in our previous class. When we calculate this, would you please use your calculators and tell me what will be the resultant of Cx and Cy? 5.15. 5.15, thank you so much. And the unit is dips. So because the problem is clearly saying that the pin C is under double shear, I'm going to say because the pin C is under double shear, I'm going to divide the force C by 2, in order to calculate the shear force inside the pin. And that will make the shear force in pin equal to 5.15 pips divided by 2, which is gonna be 2.58 pips, I guess. So how can I design the, so now we analyze. This process is called analysis in engineering design. You calculate the amount of the force that is going to be supported by the pin. So that pin should support 2.58 kips of shear force. This is what we know from our analysis. Now it's time to design. So how can we design? We actually use the fact that the shear stress in the pin cannot exceed the allowable stress of 10 kPa. We're going to use this fact. So I'm going to say that the shear stress in pin, which will be shear force in pin, it's going to be the shear force in pin divided by the area of pin that we do not know. So it's going to be 258 kips divided by the area of pin. So this is the difference between a design problem and an analysis problem. In design problems, always some information is missing. Here the area is missing. We do not know the area. But we know that this shear stress cannot exceed the allowable shear stress. So this is actually the design rule that we're gonna use in this class. As I said, just a limited amount of time we're gonna dedicate to this design of simple members or simple connections. So this is the rule that we're gonna use. The shear stress in the member cannot exceed the allowable shear stress. And this is given as 10 KSI in this problem. So from here, we're gonna calculate the minimum value for our area of pin. Could you please calculate that? How much is this? 2.58 divided by 10. 2.258 inch squared. And from here we can actually, because the problem is asking to determine the required diameter of pin C. So the problem is asking to determine the required diameter of pin C. So for that, I'm gonna actually use we'll convert the area to a formula that contains diameter. So diameter of pin squared divided by 4. This cannot be less than 0.258. And from here, the diameter of the pin should be larger than or equal to how much? 4 times, would you please calculate that? 4 times 0.258 divided by pi taken to the power of 0.5. How much will that be? Yes.
0.5759.
Thank you so much. So it's going to be 0.57. I've got 0.573, but that's okay. So this is going to be our design. Let me just highlight this as well. So the meaning of this inequality is that when we actually select that bolt, because there are normally in engineering application, bolts come in some specific diameters. So we have, for example, bolts with a 3/4 inch diameter or 1/2 inch diameter. So this inequality says that whatever bolt that we select, its diameter cannot be less than 0.5 inch diameter. For example, we can pick a 3/4 inch diameter bolt, that's going to be fine. Is there any question about any parts of this problem? Any question about each of these 2 parts? Is it clear? Is there any question in general about calculation of stresses so far. So if there is not any question, let's take a look at the problem that we have in the next page of the handout. And for this problem, I need to actually define another type of stress, which is actually specific type of normal stress, but we're gonna define it shortly. So look at this system over here. So we do have this is a typical kind of component that we see in structures, especially in buildings and bridges. So we have beams that supporting some weight, and that weight should be supported by some vertical members to transfer the load all the way to the ground. So we do have this kind of load transfer mechanism in, as I said, in buildings and bridges a lot. So here we do have a column that is supporting the weight of a beam. And the problem is actually asking to design the plates. So the force in the beam is not directly transferred to the column. There is a plate between the column at the top and the beam. So the load inside in the beam is first transferred to that plate, and from that plate is transferred to the column. So the problem is saying actually, the steel pipe column shown has an outer diameter of 150 and inner diameter of 120. And the load imposed on the column by timber beam is 150 kilonewtons. So there is actually a force that is applied from the timber beam to this column, which is equal to 150 kilonewtons. And so this is actually the piece of information that I was talking about. Circular steel bearing plates transfer this load from the beam to the plate, from the beam to the column, from the beam to the column, and then from the column to the ground. So I try to highlight these two plates at the top and bottom. So as I said, the load is not transferred directly from the beam to the column, neither from beam to the column nor from the column to the ground. There will be a plate that is used. So, what do you guys think? In this problem, the information that is given, it is asking to determine the average bearing stress at the surface between the column and bearing plate. That's the first question in this problem. So far we talked about normal stress and shear stress. We never talked about the bearing stress. It looks like this is another type of stress that needs to be defined by us. So for that, this is why I'm gonna first, actually let's do this. I'm gonna define this type of stress at the back of the previous page of the handout. I'm gonna first define it and then we're gonna calculate it. So bearing stress is actually a compression normal stress. So if you guys recall, the normal stress, okay, we have two types of normal. We have two types of stresses, normal stress and shear stress. Normal stress itself can be in two forms, either tensile or compressive, either tension or compression. So this bearing stress is a compression normal stress. But so why do we call it a bearing stress, not a normal stress? Because it occurs on surface of contact. Surface of contact between two separate interacting members. So a bearing stress is actually, this is actually the definition of bearing stress. So stresses that we define so far, the normal stress and shear stress. Excuse me guys, when you talk to each other during the lecture, even if you talk very, it can be heard, and it's gonna create a noise. I appreciate if you actually do not speak during the lecture. I appreciate it. Thank you so much. So I was saying that, the normal and shear stress, when we define them, they actually occur within the material. This was the reason that we defined this concept. So it's intensity of force. It's actually intensity of internal forces. So in all the problems that we have solved so far, we actually first calculate an internal force, internal load, internal shear force, internal normal force, and then calculate the stress. This is the actual meaning of stress. However, sometimes we have some forces that create at the surface of contact, as a contact between two separate objects. So for example, when I press this marker or press this mop on the table, clearly I'm applying some pressure on the table. At the surface of contact, there will be some pressure creates. Are we able to calculate that pressure? The answer is yes. We call that pressure bearing stress. And we can calculate that bearing stress through this equation. So we can show it with the letter sigma with the subscript b, so it's going to be sigma b, and it's going to be equal to the force, which is the vertical force or the normal force at the surface of contact divided by area, divided by what we call bearing area. Bearing area is the actual area of contact. So in these kind of problems, in the problems that the calculation of bearing stress is involved, we just need to correctly and accurately identify two parameters. Number one, the normal force, clearly. If it is given, we can directly use that. If it needs to be calculated, we can calculate it. The second parameter is to clearly and correctly identify the surface of contact. What is the actual surface that is involved in the load transfer between the two objects? That's the surface of contact. In this problem here, would you please tell me what is the surface of contact between the column and bearing plates between the column and bearing plates? It means that here, either here or here. Can you guys tell me how does the surface of contact look like? So, yes.
The area of the outer diameter minus the area.
Exactly. So in surface of contact, so the bearing plates are solid plates. In this problem, they are circular plates because the column is circular. But normally in structural application, there are square plates or rectangular plates. Here there are circular plates, but the column is a hollow structural shape. It's like a tube. Our column is a tube. It's not just a solid element. So our column has an area that it can be schematically shown like this. is gonna be, you know, we have material only in this part, only, in the, diameter between the outer and inner diameter. So the surface of contact looks like this, not the entire area of the plate clearing. Only this surface is the part that is interacting with the plate. So we can say that the cross-section area of the pipe cross-section area of the pipe will be pi over 4 times the outer diameter squared minus inner diameter squared. And could you please calculate that?
6,000.
Thank you so much. So it's going to be 6,362 volts, right?
Yeah.
And the unit is going to be millimeter squared. Thank you. So how can I calculate the bearing stress? The problem is asking determine the average bearing stress. So sigma bearing in average is going to be the normal force, the 150 kilonewton that is applied to the column. This force is actually directly applied to the column and is being supported by the column. So it's going to be 150. I'm going to write that in Newton divided by the area, which is 6,362 millimeter squared. Could you please calculate this and tell me what the unit will be?
23.58 Pascal.
Exactly, perfect. So it's going to be 23.6, and the unit is going to be Newton per square millimeter. The other name for Newton per square millimeter is going to be megapascal. So if I use instead of Newton, I wrote 150 kilonewton, the stress unit will be, or would be in GPa, not the MPa. So, but I converted to Newton, so Newton per square millimeter is equivalent to MPa. So, this is the answer to the first part of the problem. The average bearing stress, both at the top and the bottom of the column, is going to be equal to 23.6 MPa. Is there any question about this part, about the concept of bearing stress? Is that clear? How we calculate that? Yes.
So very stressing. Why are we looking at the stress on the top half of the column too?
So top and bottom of the column, not top and bottom. So you're where are you referring as the bottom here?
As the bottom very like towards. So top everything is the one with the arrow. The one below that's highlighted is the bottom.
This is what I mean by top bearing plate. This is what I mean by the bottom bearing plate.
Yeah. So why are only taking the top one to account not the one
It's going to be the same. So this bearing stress on this at the top of the column and bearing stress at the bottom of the column, not bottom of the bottom plate. Bearing stress at the top of the column and bottom of the column both are equal and both are equal to 23.6.
Oh, okay.
This is what I try to highlight over here. Because the bearing area at the top and bottom are the same, and axial force is going to be the same. There is actually an important assumption over here that there is not any bending moment applied to this column. So that load, that 150 kilonewton that I'm showing, that's the assumption in this problem. That is exactly passing through the centroid or center of that circle. So we only have one axial force. That one axial force is continuously, is constant throughout the whole system. It's passing through the top plate, it's passing through the column, it's passing through the bottom plate. So the force is constant. And bearing area at the top of the column and bottom of the column are the same. So the bearing stress at the top and bottom of the column are the same.
Okay.
Yeah, good. this is an important question actually. Height of the column is gonna be important, definitely it's gonna be important, because it defines a parameter that we call it slenderness of the column. That is gonna be important for another type of failure and phenomena that we call it buckling of the columns, something like this. So this ruler is a better object to actually demonstrate. So when I apply a compression to a column, it can, without failure of the material, without any failure in the material, it can buckle like this. Because you agree that we can actually simulate the cross section with a rectangle. One side is very long. I think none of us can actually bend the ruler in this direction, but we can easily bend the ruler in the other direction. So that's why if it is used as a compression member, it is susceptible to buckle in this direction easily with a very, very small load. That's another, and definitely in design of column, the height must be considered. I'm happy that you asked this question. So this is actually some sort of theoretical, some sort of problem. We're assuming that the buckling is not an issue over here, probably. The height has not been given. The person who has designed this problem has the reason for not specifying the column because we didn't want the buckling to be an issue over here. So we assume that buckling is not an issue. Yeah. Any other question? So the next part, so the first part was an analysis problem, calculate the stress, so we calculate that stress. The second part is a design problem. The allowable bearing stress is given and we are required to calculate the area or design the bottom plate, which is actually, and this is also an important, is a design that should be done by a structural designer actually. Design of plate is one of the jobs that a structural designer should accomplish. So the problem is actually saying the average bearing stress between the plate and ground cannot exceed 3.25 MPa. That's a design requirement. That's a design criteria that is given. That stress cannot exceed 3.25. It is important, so as you can see, the allowable stress here is defined specifically between the two surfaces. So for example, maybe the criteria for the timber and the bottom plate is different. But the criteria between the ground, that most of the time is actually concrete, and the column is actually, not most of the time, all of the time, it's a concrete foundation underneath the column. So that stress depends on so many parameters, but it is actually given to us, 3.25 MPa. So now we are asked to determine the required diameter. So we are asked to design. So this is what we're going to, could you please tell me, now we are focusing on this area. Let me just highlight it with, now we're focusing on this area between the bottom plate and the ground. Could you please tell me how does this area look like?
Solid circle, isn't it?
Exactly. Thank you very much. It's gonna be a solid circle because, as I said, the plates are solid circles. So it's gonna be something like this. Definitely it's gonna be larger than the column diameter, but it is gonna be solid. Because that entire surface is in contact with the ground. So, number two, so how can we actually design this plate? We need to, write down the equation for bearing stress. So what do we need? We need the area of this surface of contact. So I'm gonna say that the sigma bearing which is going to be, again, equal to 150,000 Newton, because the axial force is going to be constant between and it's going to be constant, divided by the unknown area of the bottom plate, whatever it is, that should and could not exceed 3.25 MPa. And from here, I can say that the area of plate should be actually larger than or equal to 150,000 Newton divided by 3.25 Newton per square millimeter. Could you please calculate this?
46,153.8.
Thank you so much. You're correct. I got the same number, so 46,154 millimeter squared. So it means that, you know, the area cannot actually be lower than this. I'm gonna convert the area to this equation. Instead of area of plate, I'm gonna use the diameter of the plate. And that should actually be larger than 46,154. And from here, could you please tell me what should be the minimum value for the diameter of the plate? 242 millimeter. Thank you so much. So let me just, you know, I try to show these two varying areas on our schematic, but let me just write down, you know, verbally what I mean by this varying area. So this is actually the varying area between column and plate. This is the varying area between plate and ground. The bottom of the bottom plate and ground. Is there any question about this problem and the solution? Any question about the solution about this problem? Any question about the subject of stress in general? So let me just tell you, we discussed normal stress, shear stress, and bearing stress. And we discussed some examples, some simple elements that we can calculate these stresses for. This is what we have discussed so far in this class. Calculation of stresses, definition of stresses, and calculation of stresses for just simple problems. Any question? So, can you guys tell me what was the objective of this class? One of the main objectives of this class that I mentioned from the beginning of the semester. We want to can anybody tell me? Do you remember? So what do we want to accomplish? Yes.
I'll better describe the behavior of beams and trusses.
Exactly. Mechanical. So I mentioned earlier mechanics of beam elements, truss elements or prismatic bars, and also shaft to circular section subject to torsion. That's definitely, this is what I said, mechanics. But I also, then in definition of mechanics, I always mention that we would like to calculate deformations in this class. So we would like to know what is the relationship between the force or load effect, either bending moment or axial force, and the deflection, angle of twist, and these kind of parameters. So load deformation is actually an important subject, an important relationship that we are interested in. This is our objective. We would like to know if I compress this member, how much it will compress. And if I actually stretch this, how much it will be elongated. These are the questions that we would like to be able to answer in this class. So in order to answer these questions, we need to define another quantity, which is actually similar to stress, but this time we call it strain. So stress was intensity of force, strain is going to be intensity of deformation. Let me just so I hope that you guys remember from from our first class, I used that surgical block and tried to show the deformations of these squares on that surgical block. So if you guys remember, that square changed to a rectangle like this, and this rotated square changed to a diamond like this. Excuse me. So this is actually, this was a demonstration to show that deformations can have two forms. Changing the length, changing the angle. So we have, as you can see in the first, on the left square, we see changing the length. We see changing the length in the longitudinal direction and changing the length in the transverse direction. And by direction, I mean direction of loading. So loading is longitudinal, or the length of element is increased in the longitudinal direction. The length of this element is decreased in the transverse direction, or in the direction transverse to the axial load, or to the load. But this second element, it does not change length, it actually changes, the angles are changing. You guys might ask, even here clearly we see change in the length. Why you insist on saying that we only see change in the angle? Does anybody have an answer to that question? So let me just repeat my question. This is actually completely a reasonable question by you guys. If you say that even in that right element, we see both. So I clearly actually everything is changing actually. But I'm actually insisting that we see, I'm actually insisting on changing the angle, yes.
If you choose a point in the middle of each line of the square, constant.
It could be like that, but I just want to say another important thing here. Yes, would you like that? Actually, this is the answer that I had in my mind that I wanted to mention, that in both of these two demonstrations, these are exaggerated deformations. In this class, in the entire class, the deformations that we're talking about are very, very small deformations. They are barely visible. So this is actually why did I use this water noodle or this ruler or that surgical glove? Because these are soft material, I can actually deform them easily. So these are only used for the sake of demonstration. The actual material that we're going to work with, they are hard material. They're difficult to deform, like metal, like steel, sometimes concrete, timber, masonry, these kind of material that we're going to work with. So we do not see these kind of exaggerated deformations in this class, at least for the engineering elements that we discussed in this class. Do they happen in reality? The answer is yes, but it's beyond the scope of this class. So we're not going to consider the large deformations, in this class. So our focus is on small deformations. So by assuming small deformations, yes, this element is not going to be subjected to any normal deformations or any change in the length. And for this one, we see, this one clearly we do not have any change in the angle, so we do not have to actually be worried about this one. So, with this introduction, I would like to define two important engineering quantities. I'm going to define, intensity of deformation. So I'm going to first focus on change in length. So how can we define the intensity of change in the length? We can define it through this parameter of normal strain. We call intensity of change in the length, normal strength, and we show it with a Greek letter. In this class and many engineering mechanics books, it is shown with a Greek letter of epsilon. So let me just, I do not write epsilon like this. I write epsilon in this class like this. So this is epsilon. And how can we actually define it? It's going to be changing the length divided by the original length. So it's going to be the new length, changing the length divided by the original length. So if we call the original length L1, and the change in the length is delta L, changing the length in the longitudinal direction along the line of axis of member. If that is equal to delta L, we need to divide the delta L by L1. And we're gonna say that it's gonna be the new length minus the original length divided by the original length. So, or, you know, we can show it like this. If we actually say that this is going to be the change in the direction, change in the length in the normal direction, or the direction normal to the cross section, it's going to be this delta N divided by L1. So this triangle sign over here, this is another Greek letter, we call it delta, so it's going to be delta L divided by L1, which is equal to new length minus original length divided by the original length, which can be also written as the deflection in the normal direction divided by the original length. So this is how we can calculate the average normal strength. You guys might ask why you're emphasizing that this is average normal strength. I'm gonna answer to that question in the next page of this handle. So if we actually measure the change in the length or consider the change in the length for very, very small elements, that's gonna be, this way we can actually calculate the strain at the point. But if we actually define it for an element with the large length of L1, we need to use the term of average. So it's gonna be, this is actually the average normal strength. But I just mentioned that deformation is not only in the form of change in length. We might have, so let me just highlight the definition for normal strain first. So it's going to be elongation or contraction in a line of segment per unit length. That's what we mean by intensity of change in length. But how can we define, or how is the intensity of change in the angle is defined in engineering mechanics? So we call that shear strain. We show it with the Greek letter gamma, that I write it like this. Gamma. And we're going to define it as the change in the angle that occurs between two line segments that are originally perpendicular to one another. So let's assume that at a specific point in a material, I do have two line segments, like this segment and this segment. So as I think you guys agree that these two segments are originally perpendicular to each other. So these two segments are originally perpendicular to each other. The angle between these two lines are 90 degrees, but after deformation, the angle changes, and we have a new angle between these two segments. So AD, from AD, this line goes to AD prime, created over here. How can we define the shear strain at point A? This is gonna be the, again, the definition for average normal shear strain if the change in the angle are actually or not that small. We can say it's gonna be pi over 2 minus 5. It's gonna be the original angle minus the new angle. This is the definition of shear strain. Yes.
So with the first one, the normal strain, if it's length over length, does that make it unitless?
Exactly.
So it's like,
Even this one is called unitless, although it has a unit of angle. It's gonna be radians. We're gonna report it in radian for shear strain. But that one, even that is considered, it's because radian angle is not one of the major units of the length, mass and time. So it's gonna be, that is also considered unitless. So, how can this be calculated? As you can see, in order to change this angle, this segment AB has moved to a new location, AB prime. So we do have a movement of point B from B to B prime. If we show that with delta S, we can say that delta S is displacement of the top of, or the top edge with respect to the bottom edge of the elements of material. Please write down all these terms. So actually, this is the elements of material that we're considering right now over here for this definition. And the displacement of the top edge with respect to the bottom edge has been shown with delta S. In our next class, we're gonna actually discuss what is going to be the relationship between that change of angle and the delta S that is called the shear displacement. We're gonna actually discuss it again.
That's the lower constriction.
Any questions, guys?
So, delta is coming in time or no?
So thank you very much. And see you guys.
It's not the